Morning, everyone. So what I want to look at in this lesson here is just to recap with you a really common technique that we use in chemistry that's referred to as a titration. So just let me jot it down here. For a titration, pretty much it's a technique used to find some unknown concentration. Now, when we had introduced this back in grade 11, it was already in the context of acid-base titration, so it seems fitting as we're in a chapter of acid and bases, we're just going to have another look at this. Let me just recap with you how this technique works here. In terms of the glassware, usually you have a burette. So the burette is a long glass tube. Usually you have the 0 mark up top, 50 ml down at the bottom. Usually I would tell people fill in the burette something more than half. Because the numbers themselves are sort of upside down, you would initially take a volume reading. So this is the initial burette volume. Let's say for argument's sake here, this is my VI. Burettes can be read to 2 decimal places, and let's say I'm exactly at 10.00 milliliters. Okay, so I'm at the mark, bottom of the meniscus, it says 10. Does that mean that there's actually 10 milliliters of solution in the burette? No, because we have the 10 mark here, the 50 ml mark down there. It's actually some 40 or so. You don't need to do the difference. You just figure out what does the burette say right now. If you remember, after our titration was done, there's a stopcock valve at the bottom. You can basically open and close it. After the reaction is done, the liquid level will now be a little bit lower. You're going to take some final burette reading. So final reading, let's say it's VF. Totally make up a number right now. 32.14 milliliters. And basically, I know even when the line is at the 32, it doesn't mean that the solution is actually, there's 32 mils in the burette. Basically, what you're going to do is you're going to find the difference. This is called the titrant, the chemical that I'm actually dropping into the other chemical here. The titrant is given by the difference in volume. So if this was the case here, I have my starting and my ending volume here. I actually subtract these two numbers from each other here. So 32.14 minus a nice 10 gives you just 22.14. And it's actually that difference that we actually added in for the solution. We are doing this as acid-base titration, so the reaction that we're interested in is going to be between, let's just do a strong acid, strong base titration for now. So hydrochloric acid with sodium hydroxide, make sure we have a balanced equation. Sometimes the mole ratio will be 1 to 1. Let's start off with this. In case it's not 1 to 1, I would just balance the equation. It really doesn't matter which solution you put where. It also doesn't matter like which one I don't know the molarity, but the key for this is you always need to know one of the molarities. So in the titrations that we've been doing so far, maybe I have a bottle. It's labeled question mark molar HCl, right? So I have a certain unknown molarity. I don't know if it's really concentrated. I don't know if there's a lot of H plus in here, but I do know that the chemical is HCl. So currently here it's a question mark molar for HCl. Because I'm going to be looking for the unknown amount of HCl, I better know the NaOH concentration. If I know the concentration of NaOH, we refer to this as a standard solution. A standard solution is one in which we have a known concentration of it. We'll talk more about that in a second here. Let's just say for argument's sake here, the NaOH was 0.1235 molar. The whole point of doing a titration is to be really, really precise. So we're going to want burette readings to be as many decimal places as possible. If I want to know the concentration, I want to know it to a really good precision. I might even know approximately what the HCl is already, but by doing a titration, I can actually get more significant figures. So let's just put the base in the burette, just for argument's sake here. So we have 0.1235 molar NaOH. Again, for a titration, one of the chemicals, you have to know what the molarity is. So I know how much volume I'm going to drop in based on this burette here. I did my difference in volume here. Usually for a titration, you do the titration a couple times. So sometimes they call it titra 1 or trial number 1, trial 2, trial 3. The reason why we typically try to keep the acid and the base concentration to be relatively the same is I know I have this bottle of acid just sitting around here. I'm not going to be sort of destroying the sample in an effort of trying to find the molarity. What I'm going to do is I'm going to pull out a few what are called aliquots. So if you imagine, you probably pour this out into a small beaker first, but what you can do is you can pull out a small, our pipettes are usually in a 10 milliliter or 25 milliliter aliquot here. Basically what we're going to do is we're going to pull out a small fraction of it. Let's do the smaller aliquot. So let's say 10 milliliter. Alicot is just a name for a small sample, right? My bottle could have been maybe 4 or 5 liters or so, and I'm only going to test 10 at a time. That would guarantee me that I'm actually not going to need that much base to kill off the acid here. I'm going to be able to calculate the initial concentration of the acid before, because concentration is intensive, even though I would have destroyed this sample. In figuring out what the molarity of the hydrochloric acid is in the Erlenmeyer, I can backtrack and I can figure out, well, if this were, let's say, orange juice here, I pour out a little bit of orange juice, the taste of the orange juice in the flask and in the pitcher is the same, concentration is identical, right? So, even though there is an unknown concentration of HCl and unknown molarity, it's totally up to me what volume we use. Usually this one here is from a pipette. So again, it's either 10 milliliters or 25 milliliters. Usually you prepare this a couple times here. So maybe during my first titration, I have my starting reading, I use 22.4. Essentially what's happened there is I've taken 10 milliliters of my unknown acid. This one here could very well be really concentrated. It could be really dilute, I'm not sure. Our job is essentially, we're going to drop in the NaOH here slow enough. What the NaOH is going to do for me is it's going to actually count how many H plus particles there are. If you look at the net ionic equation for this one here, pretty much the acid's job is to give an H plus, the base's job is to give an OH minus, and I know during an acid-base neutralization, it reacts in a 1-to-1 ratio to form 1 part water, right? So I'm going to start dropping in hydroxide. As I drop in the hydroxide, if it runs into H+, it neutralizes, the overall solution remains acidic. I'm looking for a really, really special point where I keep dropping in hydroxide. Oh, swirl it around a little bit here, it kills off H+, no problem. I'm looking for this next point. I want to drop in a very last hydroxide here, and basically I want to look for the point when it's actually killed off the very last acid particle there is. We're going to give this point a special name. We're going to call this, I'm going to titrate it to the equivalence point. Also sometimes referred to as the stoichiometric point. As that name suggests here, this is the point when the stoichiometry is obeyed. This is the point when you have no limiting, no excess. You've exactly killed off all the acid particle. So this is when your moles of H plus has equal to the moles of OH minus. Right? The implication there is that there's actually no excess. Because there's no excess, it just boils down to a stoichiometry problem. Now, I had no idea going into this how much H plus there was. That's my whole goal in this experiment. If this thing here were really concentrated, there's a lot of H plus, I'd just be able to see that, oh, I need to toss in a lot of volume of base before this point happens. If it was really dilute, there wasn't a lot of H plus to begin with. It doesn't take that much volume of titrant, and it's already hit equivalence. No doubt we will always hit this equivalence point. So either think of it as moles of H plus has canceled moles of OH minus. Another way of framing that is you can say the moles of acid and base, they follow the mole ratio. Now I know in the reaction they have to follow the mole ratio, but what I'm implying here is, let's say right now here the mole ratio here is 1-to-1. So whatever unknown amount of HCl, whatever number of moles, maybe it's 2 moles, at the point here when it follows the mole ratio, the NaOH also needs to be 2 moles. That's when the H plus is cancelled OH minus. The reason why I state it like that is sometimes your acid may be, let's say H2SO4, it's a 1-to-2 ratio. Well, I don't want to have equal moles. I might need 2 moles HCl would need 4 moles NaOH to actually react with it if it was H2SO4. So it needs to just follow the mole ratio. So again, there's no limiting. The stoichiometry ends up working out. So even though chemically speaking here, there were a lot of other little tricks here and there trying to figure out what these numbers are, at the end of the day, it boils down to a stoichiometry problem. We did see a titration already back in chapter 3 for what's called the chloride titration. In chapter 5, in our redox unit, we'll also see a redox titration. Pretty much, they're going to change the reaction on you. This one here in this chapter is an acid-base neutralization, but the technique of actually doing the calculation is always going to end up being the same. You're going to have one chemical that's known as a standard. We know the concentration. From the volume, we're going to be able to figure out how much titrant I used. That's going to be a measure of how much unknown acid there was. I'm going to find moles. Because we are at this point here where the stoichiometry is obeyed, I can figure out the moles of my unknown, and I can utilize the initial pipette volume to find the initial concentration. So that is the general technique. Titration should be fairly easy giveaways. So let me just highlight for you some other key aspects of a titration. I mentioned here, usually you do this titration more than once. For the first one, it's sort of an approximation. I want to know roughly what the hydroxide is. I don't want to be dropping it really slow and then end up realizing, oh, it's still taking some 20 mils or so. First one will be fairly quick. You open the stopcock here, right? And then as basically you get closer to this equivalence point here, you want to just get a rough number. If you overshoot it, so be it. Because I'm already knowing, usually what you're going to do is you're going to do a second trial, a third trial. So even though I may have sort of overdone it this way, what you would do is you would take a fresh sample of Alicot. So you have a new Erlenmeyer flask here. That Alicot here would also be a 10 milliliter. Again, it's replenished with H+. Now that I know roughly what the volume of titrant that we needed is, I'm going to be a little bit more careful the next time. Because I noticed that roughly this titration, based on my numbers, it took 22.14, I just want to make sure I have enough still left over in the bread. Between the 32 mark and the 50 ml mark here, that only is 18, I probably don't have enough solution. So between one trial and another trial, there's nothing wrong with reloading the bread. So I realized, no, I'm not going to have enough left over. Let me just top up the bread a little bit. Again, the starting number really doesn't matter. So let's make the starting number here. I pour it in even more than it was at the really beginning, 5.67 milliliters. Okay. So again, all I'm doing is I pour it something more than half because I don't want to have to reload in between a trial. Every time you have to load up the bread, you're going to increase more error. So what I do is I load it all at once. I may be at the 5.67 mark here. And what I'm going to do is I'm going to try to start my titration from here. That's just what the bread says right now. Let's figure out what the bread says after the reading is done. So because I knew the first trial was about 20 mils or so, I probably toss in, I don't know, 18, 19 milliliters, really, really safe. So go from 5, you're going to open it up here, 18 or 19 mils above that here would be about 23, 24 mils. I get it, the bread reading to 23, 24, you shouldn't have hit equivalence point yet. Because the first one says, oh, I still need a couple more mils. And then as I get closer and closer to this 22 point, I just start adding it a little slower, a little bit slower, a little bit slower. I'm looking for the point when this point here is just reached. It is totally possible, whoop, I slipped my hand here, and basically there's too much base here. I would totally get this to neutral, but now there's an excess of OH minus. Now I don't have a good count on how much H+ there is. I want to add it in a slow enough fashion that the hydroxide add perfectly kills off the H+ that I have. So let's say I do that the second time here. This one here, it reads 27.65. Again, it doesn't mean that currently there's 27 left over in my bread. That's just what my bread line is at. We still need to do the difference. So we go 27.65 minus off of 5.67. Not a nice number. We get 21.98, right? You just sort of compare your number as well. The first one, if it looks like I overshot it here, good, I'm slightly under it. In this case here, I'm looking for about another 21, 22 mils or so. I'm just going to figure out, do I still have leftover in the bread here? I probably just have enough. Because 27 mark here between 50, that's about 23 milliliters. If you're a risk taker, you can just keep going. You can say, all right, so now for my third titrant, for my third Alicot here, I'm going to be starting at the 27.65, and I'm going to figure out here, well, if 27.65, you do your titration, if this 21.98 were roughly correct, I can actually have enough in the bread. And lo and behold, when you drop in the last one here, you get really close to the edge. I probably wouldn't push it to that far, but in this case here, whew, we're still above that 50 mil marking. We can still make a sensible reading. 49.59, let's just make up that number here, and I just do the difference. Minus 27.65 gives me a difference in volume of 21.94. Okay. As you do this experimentally here, there's no guarantee that, oh, the first one's always going to be bigger than the other two. Sometimes the third one will be the really off one. But our goal in this is to do a multiple trial so that we get minimize some of those random errors and we get a sense of what the average should be. The reason why I said we were really pushing it here is because the 50 mil marking is the very last marking that I have, although there is going to be some leftover solution because I don't have any markings down there. I don't have a nice estimate of, well, how much volume am I dropping it in, and therefore I won't have a good number, good reading on my volume. In this case here, even though it took a little bit of work to actually get to these numbers, you as an experimenter are going to evaluate these numbers. The first time I did it, it was 22.14. The other two times here is a little bit less, right? So maybe I would say this one here was overshot. Maybe I overdid it. That's not a really nice number. If all three numbers are all different from each other, since these are all aliquots from the same unknown HCl, I would just average all three. In this case here, because one of them is much different from the other two, and the whole point of doing a titration is to be really, really precise, you are allowed just to average the close trials. So these two trials are closer to each other. Again, it doesn't have to be successor trials. Maybe trial 1, titration 1, and titration 3 are close. You just average those two. But essentially here, this is a very common technique. You average the close trials. How do you average numbers? You basically add them and then divide it by, in this case here, 2 numbers. So divided by 2, and that puts me right in the middle, 21.96. So I did this titration 2 times, and roughly the volume that I needed was 21.96. At that point there, this boils down to a stoichiometry problem. Let's just finish off the stoichiometry. Because we are at an equivalence point, because we had no excess, I have just added enough hydroxide. I knew the standard concentration. I knew the molarity to begin with. This is the volume on average I added for the 3 trials. I only used the latter 2 trials. You're going to use the chemical that you know more. I know the volume and the concentration. Let's find out how many moles of OH minus. And again, the whole point of the hydroxide was to actually count off for me here. The moles of hydroxide is in a 1-to-1 ratio with HCl. And then using the initial volume, I can then get back to concentration. Titration problems always boil down to this. So let's just try it out here. Sometimes, even for a short answer question, they may break it up into 2 or 3 steps. They may say, find the moles of NaOH first, then find the moles of HCl, then find the concentration. They're just trying to, from their standpoint, they're trying to figure out where people are having trouble. From your standpoint, you can use that as a clue. I didn't know how to do it, but they're asking me for moles. Let's do that first, then mole ratio, then over concentration. Just for convenience, I'm going to do it all in one step here. Let's find the molarity of HCl. That was our whole job of a titration. And we're going to start off with a chemical that I know more. So I know the volume and concentration of my standard solution. I know my concentration is in moles per liter. So I want to convert this average 21.96 into liters. So let's go 0.02196. This is liters. I'm going to remind myself that that is NaOH. We're going to multiply it by the known concentration. That's why one of the solutions you have to know the molarity. 0.1235 moles for a given liter. The mole ratio says for every 1 part NaOH, there is 1 part HCl. That helps you jump chemical. We're very used to going top unit cancels bottom unit, top unit cancels bottom unit. That's all great. In this case here, I actually want to keep the top unit here as moles of HCl because molarity for HCl should be moles of HCl per liter. Now the question here is, what volume should I end up dividing by? Initially, the volume was 10 milliliters, right? That's what the acid was sitting in. Unfortunately, as I was trying to add in the hydroxide, I had to add in some extra 20 mils or so. So the final volume actually in this Erlenmeyer ends up being some 30 mils or so. That was just sort of unfortunate. That's just needed to bring the hydroxide into solution. The acid that I'm counting, the moles of H+, were actually sitting just in my initial volume. So it's important for you to note here, I'm going to have counted the number of particles. This is how many moles of HCl that I have, but this was initially only sitting in a pipette of 10 milliliters. I did that in liters. Moles over liter gives you concentration, and therefore in this case here, this one here, I'm dividing by the initial volume. I have essentially destroyed the sample in counting the H+, but fortunately because I have more where this solution came from here, if I can find out the concentration, I would know the concentration of my original bottle, and I can do more with it later on. Okay, so let's try it out here. 0.02196 times 0.1235, mole ratio 1-to-1 divided by 0.01. It gives me a concentration. Keeping track of your sig figs, notice this is really good. I have 4 sig figs for basically all my numbers here, so my concentration is now 0.2712 molar. There's no guarantee that the concentrations of one chemical and the other chemical have to be the same, right? I just said roughly I want them to be close so that, let's say I'm pipetting 10 milliliters, it should take maybe something 10 milliliters, 20 milliliters to actually titrate. If the HCl was way more concentrated, if the HCl in this case were like 3 molar here, there's too much H+, I'm going to completely empty out my bread, and I still wouldn't hit this equivalence point. So that's why we always want to do some rough estimates first, make these close, and then by doing this titration, we can end up finding the concentration for real. Okay? Just a quick caution here. Mathematically here, this looks like we have done a V1 times a C1, and then later on what I've done is I've divided by a V2. It looks very similar to the dilution kind of calculations here. I'm just going to hint at it right now. In a dilution problem, we'll do more of this next day. C1 V1 equals C2 V2. Well, if you're interested in final concentration C2, oh, perfect. Let's go C1 times V1. That's what we did earlier. And then we end up dividing the V2 over. That's your divide by V2. What you're going to be missing, if you accidentally did with the titration, is you're always going to be missing this mole ratio step. So long story short here is, even though it looks like a dilution problem, don't do it like a dilution problem. Do it as a stoichiometry problem. So I'm going to give you a case in point where this one actually doesn't work out if you do C1V1, C2V2. Let's try out another equation. Let's do H3PO4, and let's react it with calcium hydroxide. We've done a lot of predicting in the past here, so acid-base neutralization, we're going to end up forming a salt. Calcium is going to be grouped together with phosphate, and then we're going to have water. Make sure you've written the correct compounds. So calcium is an alkaline earth metal. The phosphate here is a -3, so I would need Ca3PO42. And in fact, I think I hinted at it before, for balancing a neutralization equation, basically at the end of the day, it's the H plus for the acid reacts in a 1-to-1 ratio with the hydroxide, produces 1 water. Just one acid particle, phosphoric acid here, is going to give me 3 H's. One calcium hydroxide is going to give you 2 OHs. Both 2 and 3 go into 6. So let's just double this one to make it 6 H's. Let's triple this one. I'm going to have 6 H pluses, 6 OH minuses, and this should give you 6 waters. At that point, this one should be fully balanced off. Okay. Let's say we've done all this in the background, right? I set up, I'm dropping one thing into the other. I'm watching for when the equivalence point is reached here and when the stoichiometry is obeyed. Let's say this time I don't know the molarity of CaOH2, but I basically flip everything else around. Maybe I had pipetted in 25 milliliters of acid. The concentration of one of them has to be a standard, so I have to know this one. So let's make it 0.5716. Totally make up a number there. And then for the other titrant here, maybe I have dropped in, right, I did a couple of trials, I figured out what average volume I'm needing, and let's say I'm requiring 32.74 milliliters. Okay. So practically speaking, it took a little work to actually get to these numbers. Maybe this number here was from a pipette, right? So just pumping it into the Erlenmeyer flask. The other one here was from the long glass tube, it was a burette. But noting that we are at equivalence point, same procedure. We're going to take the chemical that I know more, the volume and concentration. Let's find moles first. It's the mole ratio step that we're going to get from a balanced equation. This one's a scary, it's a 2-to-3. And then we're going to use the final volume to end up getting concentration. So again, the whole point of doing titration, let's find the molarity of calcium hydroxide. Sometimes they even tell you what the concentration is. They might ask you, well, what volume will I need to end up reaching equivalence? Similar strategy here. Once you find moles, you just utilize the last number and find what the unknown is. So in this case here, I'm starting off with one I know more, 0.02500 liters. That's my H3PO4. For one of the solutions, as your standard solution, you need to make sure you know the moles per liter. So you need to know the concentration. This time the mole ratio is a little bit scary. So 2 moles of H3PO4 for every 3 parts calcium hydroxide. Again, a little bit strange math here. I'm just letting you see it a couple times here. Liters cancels liters, moles cancels moles. I do actually want to keep the moles of calcium hydroxide on top, but I want to divide it by liters on the bottom. Remember, the liters in total inside my Erlenmeyer at the bottom would be 25 plus the 32. I'm going to have some 55 milliliters in my Erlenmeyer. I don't want the final volume. It's sort of unfortunate that by dropping in one solution, I sort of diluted the sample here. I know all the hydroxide that I counted used to just be in my 32.74, so I'm going to divide by the initial volume. This is why sometimes in a titration, they might say, oh, it's actually okay for you to actually add water. Sometimes the acid and base splashes up on the outside. You're going to use some water and actually spray down. Just spray down the sides. Sometimes a sort of half droplet forms on the burette. It would have been counted in the readings, but it's not quite dropped in yet. You use a spray bottle again, and you just sort of squirt that water in. Wouldn't all that water end up diluting this? Sure it would. But if you remember for all our titrations, I never really am concerned with the final volume in the Erlenmeyer. That just is used to bring, in this picture here, the hydroxide into the H+. The H+ initially was only in 10 milliliters. We are ending up dividing by the initial volume anyways. So let's just do that here. We're going to go 0.025 multiplied by 0.5716. It's always the mole ratio step that you're going to lose if you do C1V1, C2V2. So don't do it that way. Do it as a stoichiometry problem. Times 1 divided by 0.03274. Okay, and there we go. We got the concentration. Again, we have really nice sig figs here. All of these numbers here are 4 sig figs. What about the sig figs on the 3-to-2? Well, the 3-to-2 actually came from the recipe. The recipe, these numbers here are exact. They will not limit the procedure in any way. So the concentration I get out of this, double check my numbers, I'm getting 0.6547 molarity, and that's how you find the unknown concentration. If I had given you the concentration, oh, the calcium hydroxide is 0.6547, you could have used moles, used the concentration, and that could actually help you find liters as well. But pretty much it boils down to a stoichiometry problem. Now, lastly for this lesson here, I just want to introduce a few other technical notes here. We are looking mainly at this really important point here called the equivalence point. I want to know when to stop. I want to know when my indicator is going to start changing color to tell me when to stop here. The reason why we need an indicator is, unfortunately, both HCl NaOH, both the H3PO4 calcium hydroxide, both of them are actually completely colorless in solution. I wouldn't know when to stop. So what I'm going to do is I'm going to cheat a little bit. So if you just think for another example here, back to my NaOH HCl titration. Again, the problem is both of these are actually colorless. I know I'm looking for that point when basically I've dropped in enough hydroxide that I basically killed off all the H+. I want to stop at this point here. But being completely colorless here, the salt that I get as table salt is fully dissolved, I'm not going to have any indication that the reaction is done. So if you remember from our titration setups here, we actually throw in a chemical called an acid-base indicator. We're going to do a section on indicators later on in this chapter. But pretty much for an indicator, the indicator we used was phenolphthalein. It was just one particular chemical. For an indicator, we're going to see that it actually ends up in equilibrium. It's a reversible reaction. And for every chemical indicator, it has a relatively acid color and relatively basic color. Every indicator will change at a different pH reading. In acid, phenolphthalein actually remains as colorless. So what you would do is you drop in a few drops of this indicator. It just needs to be present. It doesn't need to be high concentration. At first, when I have a lot of H+, it's going to stay colorless. For this indicator, as you start neutralizing the H+, it's going to start converting some of these colorless particles over to pink. So as you get closer and closer to the equivalence point, closer and closer to that stoichiometric point here, when it starts turning pink, you know when to stop. So I drop in the first hydroxide. The hydroxide finds H+, overall still acid. The indicator stays colorless. You drop in another hydroxide here. It kills off the H+. Now, as it gets harder and harder to form H+, the pink color starts staying for longer. What's going to happen here is now I'm going to drop in that one final drop of hydroxide, right? As I drop in the hydroxide, because I've already neutralized at equivalence, there's no more H+ around. Now the hydroxide can't find any more H+ to run into. Now it's suddenly basic. Now the indicator is suddenly going to shift over to base. Now what I want to avoid is dropping in too much base all at once. It's totally possible to make the solution pink. It's really easy. Just drop in a ton of base. But unfortunately, if I drop in a ton of base, if I have an excess of hydroxide, yes, the indicator will be a really, really pink color. But now I'm going to have an excess of OH minus. Now my stoichiometry, my mole ratio may not be exactly matched up. I would actually have an excess of hydroxide. So what I want to do is always want to add it slow enough. As I'm noticing that in this case turning to pink is staying longer and longer, I want to stop at the point sort of right before it goes to a full pink color. It's usually going to be a mixture of these two colors here. We're looking for sort of the faint pink color, a very pale pink color. Usually if you hold it up against a white background, you can just see the last trace of pink. And usually we want the color to last for some 15 seconds or so. Nothing magical about that 15 seconds here. It's all relative anyways. We're going to find sometimes, well, there's carbon dioxide in the air here. That also is acidic. That can also interfere with where the color change occurs. But if the color changes and it stays for a little while, that's when you know when to stop. For an indicator, the point where color changes is actually referred to as its endpoint, or also referred to as its transition point. So, hypothetically, if I use a wrong indicator for my titration, I can get the indicator to change color, right? I can get it to go from colorless to pink, no problem. But if this is nowhere close to the equivalence point that I want it to, the color change doesn't tell me any information. So it's much smarter if we actually choose an indicator. Every indicator will have a very unique pH where it actually changes color. Choose a right indicator to correspond with the right mixture that we're talking about. So phenolphthalein is very common. We actually have a chart for it later on. Phenolphthalein changes somewhere between an 8.2 and a 10.0 for pH. And just for simplicity, even though it gradually changes over this, I call it a pH range at which it changes color, usually what we do is I know pH is on a logarithmic scale, so it's not quite even. It's not quite, well, the first step will be easier than the other step here. But usually I just say, well, it's colorless here until 9.1, and then bigger than 9.1 there, it's now switched to fully pink. So more on indicators later on. We want to choose an indicator. Let me make that note right here. So you want to choose an indicator that changes color. We'll talk about why and when it changes color in a later lesson. Changes color close to the equivalence point. So the stoichiometric point here where there's actually no excess. Again, you can be silly and you can choose a indicator changing color, but if it doesn't tell me anything about the solution, that's actually no good to you. Right? One last practical aspect that I want to just introduce to you. Our whole goal is to start off with a standard solution of NaOH. So that is a solution that I know the concentration. I can use this as a verb here. I'm using something that I know the concentration to find the concentration of the HCl in this case here. My process here is I'm actually using the NaOH to standardize the HCl. I want to find the HCl concentration. Once I know the HCl concentration, I can then use this HCl concentration to standardize other solutions as well. Because in a titration, we always need to start off with one thing that I know to calculate for the other unknown molarity, we then end up with the sort of chicken and egg question. Well, how do I know the concentration of NaOH? Well, I could have titrated it against another acid where I know the concentration. Well, how would I know the acid? Okay. Fortunately for us, there is another way of finding the concentration to a really, really high precision, and that basically involves making solutions. However, most of the chemicals that we can think about in making solutions, most of those chemicals don't act as a really good primary standard. So the chemicals that we can actually start off with, that when I make a solution that I'm really, really confident to a lot of sig figs what the concentration is, we refer to this one here as a primary standard. So I'm just going to give you this definition here. For me, a primary standard, just think about this is a solid that is solid with very high purity and stability. It's a chemical that pretty much keeps to itself. If you leave it out exposed to the atmosphere, it doesn't react with water, it doesn't absorb water, it doesn't react with carbon dioxide. It pretty much keeps to itself, so that if you put this solid here on a balance, let's say I weigh out 1 gram of the solid, because this chemical is pure, when I weigh out 1 gram, I'm pretty sure that this 1 gram is completely this chemical. Let's compare it to something that's not a good primary standard. NaOH is actually not a good primary standard. NaOH here actually comes to us in the form of pellets. You can no doubt weigh out 1 gram, no problem. The problem if you ever work with NaOH is you realize that even though it comes to us as pellets, you leave it out over maybe 5 minutes, 10 minutes, and it's already absorbed some moisture. It's already started embedding some extra impurities in there, so that sure, experimentally, you may still be able to weigh out the 1 gram, sure, you may still be able to dissolve it in solution and whatnot, but based on those impurities, maybe not all the 1 gram is actually NaOH. So primary standard is a good starting ingredient because it's so pure, because it doesn't react with water, doesn't react with carbon dioxide. It's a nice sample to start off with. I can make a solution of this. I'm going to just draft how that works. You take your powder. First thing that we do is we pre-mix it in a beaker. Beakers have a nice wide mouth, so you can use a stir stick and you can mash up the powder. Unfortunately, beakers, the markings are not really precise. So what you would do is you would transfer that into a volumetric flask. A volumetric flask here has a rounder bottom. The volumetric flask only has one single mark. Let's say this is a 100 ml volumetric flask, but that single mark there is really, really well calibrated for. So what you do is you take the pure primary standard, that's a solid, you're going to drop it in, you're going to dissolve it in something less than 100. You're going to pour that into the volumetric flask here. Just make sure it's less than 100 so that by the time you pour, rinse it out a little bit, pour that washing into the volumetric flask, eventually you can just add water directly to the volumetric. When you have bottom of the meniscus ending up hitting the 100, I now know not only this 1 gram was the pure chemical that I started with, the primary standard. I also know that the volume, in this case here, is 100 milliliters, and therefore I can take the molar mass, find moles, and then divide it by 0.1 liters. That's how I would actually find the concentration. Now earlier we had said, wait, NaOH was actually a standard. NaOH, we actually knew the concentration. I thought we just said NaOH here is not a good standard. Well, how did I know the concentration? Well, probably I started off with some acidic standard. I'm just going to give you an example of this. So what's an example of an acidic primary standard here? The chemical, we're going to shorthand it just KHP. KHP is actually the chemical potassium hydrogen phthalate. I'm just going to give you this name here. This one here, I'm going to give you the molar mass. It's 204.22. Give you the name as well, potassium hydrogen phthalate. So this one here, just chemically speaking, it can be obtained in a really, really pure form, so that whatever mass that you decide to weigh out, I can calculate the concentration really easily. So that work would look something like, what's the concentration of KHP? When I make the solution, you're going to take whatever mass, maybe 1 gram, maybe I'm going to actually use my molar mass here, 204.22. You can check your periodic table there. And if I actually made it up to 100 milliliters, I would just go 1 divided by 0.100. Again, lots of precision here. Because KHP is one of those primary standards, it's super pure, so that when I actually weigh out exactly these amounts here, in making the solution, I know this concentration really, really well. So, whew. This is actually how I get my starting concentration is 4896, so let's make it 490. I now know the concentration of my acidic standard. I can use this to first standardize a solution of NaOH. NaOH here was not a good standard. I may roughly weigh out a certain mass, roughly know what the molarity is. By doing a titration against KHP, I can know the molarity much better. And once I have that as a standard solution, then you can use the NaOH to therefore standardize other things. So it's just NaOH here is not a good starting ingredient because it very quickly absorbs water. It actually reacts with gases in the air. And that's what's going to embed a lot of impurities. So therefore, the question mark here is, I don't know whether this 1 gram is actually fully NaOH or not. There's 2 other acidic standards here. I just want to give you this list. KHP is one of them. Another acidic standard, we're going to hopefully be able to do this as a lab. So oxalic acid dihydrate. You don't need to memorize these names here, but just note there are some chemicals, the molar mass of this one is 126.07. There are some chemicals that are really, really pure. You still need to do the balance equation. So oxalic acid dihydrate, it's actually a 1 to 2 ratio with the NaOH. Well, we know how to do stoichiometry, so it's 1 to 2. We get sodium oxalate and 2 waters. So again, oxalic acid is a primary standard. Oxalic acid is a good, pure solid. So that if you make a solution of this H2C2O4, I would know the concentration really well, and I can use that to standardize whatever base in these examples I've just been using as NaOH. What if I wanted to find the acid concentration? Well, acids react with bases. I would need a primary standard on the basic side. So let me just end off with this here. A basic standard, actually surprising, really common chemical in our kitchen chemistry, which is just sodium carbonate, which is essentially baking soda. So, sodium carbonate. This one here can be left for days and days, months and months here. You can leave it exposed to the atmosphere. It really doesn't react or absorb moisture. So what's going to happen here is sodium carbonate Na2CO3. This has a molar mass of 105.99. This one here can also be used as a starting solid, make a solution, and you would actually know the concentration to a really high precision. Once that becomes a standard solution, you can use that to standardize, find other unknown concentrations. Okay, so have a look at some of the titration problems in this section here, and let me know if you have any questions. Thanks, guys.